The observed property for the gravitational vector field is that it is conservative. We will define a conservative vector field to be a vector field which is the gradient of a scalar function. So if there is a scalar function which you can take the derivative of into a gradient and you recover a vector field, then that vector field is conservative. There are vector fields who are not derivatives of certain scalar fields, so those are not conservative. Instead of calling the function f the antiderivative of the vector field, as we did back in Calc 1, we will call that scalar function the potential of the vector field f. In more technical terms, the expression which we are integrating, f dot dx, will be called an exact differential form. This might come into play later in courses such as differential equations, but for now, this is something that we do not need to worry about. The important property of conservative vector fields is that their integrals are independent of path. There is a main theorem for this section, which is the fundamental theorem of line integrals, which says that when you integrate a conservative vector field, which can be expressed as the gradient of a potential function, then the result is just the potential function evaluated at the beginning and the end points. So in this case, if your curve C is parameterized by a function r, then the resulting integral will be the potential evaluated at the end point minus the potential evaluated at the starting point. This should throw you back to the fundamental theorem of calculus, in the sense that when you integrate the derivative of a function through the interval ab, you will recover the original function evaluated at b minus the original function evaluated at a. Let us see how this applies to the gravitational force field. In the previous example, the gravitational force field was F equals 0, 0, negative mg. It is not immediately clear how we will find the potential function for this vector field, but let me tell you that the gravitational potential is the function negative mgz. It's a linear function. You can observe that when you differentiate it with respect to all variables, we obtain precisely that its gradient is the gravitational force field, as desired. This means that the gravitational force field is conservative. As such, the integrals which we calculated before were from paths between the origin and 0, 4, 4, but applying the fundamental theorem of line integrals, we may just evaluate the potential function at the end point and the potential function at the starting point, and then subtract them. Observe that when we evaluate f at 0, 4, 4, we get precisely negative mg times 4, and when we evaluate it at the origin, we get 0, so that it holds that the integral from any path connecting the origin to 0, 4, 4 of the gravitational force field is in fact negative 4 mg minus 0. And that was the result that we obtained in the previous examples.